头，一格格，一头二头。
我们开始上课。Drive the momentum fields. I want to introduce the classification on mental particles. So the idea is like to start from the grouping theory to classify the unitary irreducible representation of the concurrent symmetry of our space-time. And the particularly importance of this unitarity, okay? Because of unitarity, it's pretty hard to find the irreducible representation for the concurrent group. Actually, all the unitary irreducible representations are infinite dimension, no finite dimension. So as you can see, original classification is very physical in a sense. It just tells you what are the possible particle states can exist in our real world. And it was also labeled by the two physical parameters. One is mass, another is speed. And from this result, or original result, you can immediately get the physical degrees of freedom. Okay? It's some magic. Okay? Usually, if you start from the field theory, for example, you should do maybe a long analysis to see what are the physical degrees of freedom. But from this theory result, you don't need to just you can even see. Okay, one step. And following this, the important question would be how to embed particles to fields, okay, into fields. Okay. What do we mean by this? We know this is a famous original result, but the more non-trivial thing or the thing we are interested in will be how can see this one from the field construction. Do we want to quantize we want to embed the particle into quantized fields. We want to consider the field theory. So this is the complete stuff. So in the end of last lecture, we mentioned a few examples. Let's say scalar field, which is corresponding to spin equals 0. And we also mentioned the vector field. Okay. The vector field, then usually you might say, okay, there is 4 degrees of freedom. Okay, because mu run from 0 to 3. Okay, there are 4 degrees of freedom. Then naively you might say, okay, if your physical degrees of freedom is less than 4, then it's possible you can embed the particle into this vector field. Right? Indeed, it's true. For example, for magnets, spin 1, the degrees of freedom is 3. You can do this. Okay, you can embed the massive spin 1 particle into a massive vector field. Okay. So in that Lagrangian, there will be a mass term apart from the Maxwell term. Okay. I mentioned that. We didn't derive it. You can kind of derive it. And we end the last lecture. I introduced famous series, Maxwell's. So let's continue. So for Maxwell's theory, the Lagrangian is already known. Famous Maxwell Lagrangian, and F mu nu is anti-symmetric for mu and nu index. Okay, meaning if you switch mu and nu, then you get minus sign. Okay. Because F mu nu is defined in this table. You can say it is restricted to index, you can see this symmetry. And you can derive the equation motion from this Lagrangian. So we did before. Equation motion. And the equation motion, as you can see, to derive the equation motion, this is f squared. F is the partial A, okay? It's just partial A. 2 terms of partial A. So you can see in this Lagrangian, there's only a derivative term, okay? There's no A term. So you do variation. Then you get equation motion. Equation motion becomes partial mu, partial L. A mu, A mu. This is equal to 0. Okay. This is actually also it's nothing but partial mu F mu nu. You might see from textbook, of course. This is the term of Maxwell's equation. Okay, in terms of the variable. But this is not the all equation motion. Okay, in fact, there's because of the definition of F, there is the famous Bianchi identity. You can easily check this is the most true. In fact, this is also true. So these 2 equations put them together gives you the Maxwell 4 equations. Okay, complete the set of Maxwell equations. And the connection will be you can just find a mu with your familiar component variables. Let's say a mu will find a vector, okay, a three vector. And in this case, you can also write the E. The definition of E will be this one, and the B will be this one. Okay. And F is essentially, in terms of components, can be expressed in terms of E and B. Because it's antisymmetric. So diagonal will be 0, okay? Diagonal will be 0. So this will be E, this will be minus B, plus B. Okay. So F is nothing but the 4x4 matrix in terms of E and B, as we mentioned last time, because these are the gauge invariant objects under gauge transformation, right? And there's a more physical. Then from equation 2, which is Bianchi identity, you can easily verify there are two equations, this one and partial B, partial T equals minus partial E. Okay. These are the two pieces of the Maxwell's equation. And from the equation 1, you get the familiar vacuum Maxwell equation, which means there's no matter. If there's no matter, then you get another two pieces of Maxwell equations. So if in the presence of the charged source or matter, charged matter, these two equations will modify. Okay, if you are very familiar, because if there's a charge density, according to Gauss's law, there will be some source in there, right? For the this equation. But these two equations will not be changed, even in the presence of the charged source. Now we also mentioned that the gauge symmetry, the gauge redundancy last time. Then the immediate question we didn't solve it yet. We're going to say why. From this equation of motion, say here, why there are only 2 degrees of freedom. Okay, because from Wigner's classification, we already claimed it. We know the result, but we don't know how to derive it from classical field theory. You should ask yourself, why photon has only 2 degrees of freedom? Okay. This is the question. Next question is why photon? It's only 2 degrees of freedom. So to see it, let's start from the equation of motion. From there, start from the equation of motion. For example, 1. From the equation of motion 1. This is the equation of motion for V mu. Okay. For A mu. Here. When you write it explicitly, the equation of motion will be let's write it more explicitly. There will be partial mu, okay? F mu nu is partial mu a mu minus partial mu a mu equals to 0. See? That's about this one, okay? See? Now let's start from here to go step by step. So this is what? So this is nothing but a box a mu minus partial mu a mu. Okay. This is this equation. Now let's write it even more explicitly in terms of component. When you see such kind of equation, you see this is not only one equation, but 4 equations, right? Because there's a free index, it's not a contraction. So nu can run from 0, 1, 2, 3. So this is 4 equations. So let's even write this more explicitly. Let's write all the components. Okay. So in terms of components, this equation becomes this is the 0 component, right? This is 0 component or T component. You can check it. So it's not answer and left is left. You check it? Not that difficult. I just pick nu equals to 0. Okay. So you might say, okay, this is upper or lower index. It doesn't really matter, right? But these are the equations. Right hand side equals to 0. You can uniformly up or down the index. Doesn't matter. Okay. Now the remaining 3 equations will be the box a I minus partial I partial b a 0 minus partial j j 0. Okay. You can check yourself. That the component equations. Okay. Now what can we do? It still looks a little unclear, right? There's no immediate consequence out of these equations. Why their photon has 2 degrees of freedom? Not clear. Not clear. For example, naively you might say, okay, this is some differential equation for A0. This is some differential equation for AI. So the first may represent 1 degree of freedom. The remaining may represent 3 degrees of freedom. It's still unclear. Okay. What can we do? So we do some key observation from here. First observation is, let's look at this A0 more clearly. The first observation is the field, the A0 field. If you point the field, there's no A0 dot term in the Lagrangian. Okay? You can easily check it. Okay? Okay? Means what? Means what? This means there's no time evolution for A0. Okay? Or A0 field is not a perturbating field. Okay? There's no dt term in the Lagrangian. It means in the equation of motion there will be no time derivative or partial t squared. Okay. Okay? For A0. So this field looks like one shot. Okay, it's not propagating. There's no motion with this field, but this field is just one step determined by some boundary condition. You see, there's no propagating degree associated with this field. Okay. This is generally true. Whenever you see a field has no such kind of term, no partial t in the Lagrangian, then there's no motion. Okay. You see it? Good. Another step is related to what we mentioned last time. And this step you have to pick some convenient gauge fixing choice. Okay. Right? We mentioned last time there is a gauge redundancy. We already know that fact. Okay. There is a gauge redundancy in this system, or in this theory expressed in terms of A mu. Okay. If you express this theory or Lagrangian in terms of A mu, we know A mu is not quite unique. Rather, there's a gauge redundancy or equivalence between different A mu. Okay. If they differ by a total derivative. Okay. That's what we learned last time. Then this means there's a last time in the end of the last lecture, when students are trying to ask the meaning of this field. This field is very symmetrical field, okay? And each line represents one physical configuration, okay? Or physical state, if you want, okay? For example, some A mu, this is very schematic. Each line represents some physical configuration. So what do I mean by that? For example, one configuration of a vector field in the space-time, okay? That's what we call a configuration, okay? Configuration. And for each line, if you run over this line, means you just run over a gauge object. You run over a gauge object means you change your lambda, okay? Because A is equivalent to A plus partial on lambda, right? For different lambda, you run over gauge object, which means that this entire line actually represents only one thing configuration. Okay, okay. This is kind of redundancy in the line. Okay. Then we also mentioned that to fix this redundancy, there's a big redundancy in this system. It sometimes causes trouble. Sometimes it's convenient, but sometimes it causes trouble. Okay, because there's a redundancy. It's not a faithful describing. So in order to solve this one, we can choose a section. Section means that we choose for each line we choose a point. Okay, we choose a point. Then you throw away all the other redundancy. You see, okay, or other your mirrors, descendants, just equivalent. So we choose we choose the point for each line, then it forms the section. See, this is called the fixing. Okay, so it's fixing condition. Okay, you can understand it, right? Because A is not quite unique, but if I put additional constraint for A, okay, then I can take use of this constraint to make A more unique. Okay, that's called gauge fixing. Okay, that's called gauge fixing. The point is, often the final result does not depend on the gauge fixing. So no matter which you choose, eventually, for example, when you final amplitude evolves photon scattering, whatever in QED, this is now final result shouldn't depend on this gauge fix. Okay. Here we are facing this problem because up to here we didn't do this gauge fixing. There's still a huge gauge redundancy in this system, okay, or in this equation motion. We have to do the gauge fixing. And so there's no unique choice. Or there's a different choice, multiple choice. You can choose a particular fixing. So here we choose a particular one. Is the cluster J, AJ equals 1. Okay. Let's first try this one because this is a very convenient gauge choice, gauge fixing. Okay. So you might notice why write this index in terms of I or J. I just don't distinguish or don't operate. I try to make things more clear. I try to make everything as lower index, right? So this is the gauge fixing. This is my gauge fixing. This gauge fixing has a name. This is called what? Another name? This is called the famous Coulomb gauge. Okay. Coulomb gauge. This is called Coulomb gauge. A has some ambiguity, but the fixing condition might clear those ambiguity, right? As you can see, if I put constraint for A, additional one, okay? This might clear this ambiguity for A. And finally, down to more concrete choice for A. So we should use this one, right? We should use this. We should use this. Now, there's some there's some logic maybe we should try to clarify in the beginning. There are many conditions, right, in studying the field theory. On-shell condition or off-shell condition. Now we introduce another one, which is gauge fixing condition. So what is the priority? Which one is more priority than others? Okay, you should ask yourself. Okay. So for this question, you should understand the condition does which kind of job, right? So gauge fixing condition clear this unphysical degrees of freedom. Okay. So in this sense, it's more a prior than others. You see, because without this condition, you might get a redundancy degrees of freedom. You even didn't get a correct number of degrees of freedom in your system. So that's a serious problem, right? You see. But other conditions, some conditions may not change the degrees of freedom at all. Okay. You see. Yeah, this becomes think about it. This becomes even more important when you're trying to quantize. Okay, so when we quantize the system, we sometimes also mention that there is looks like a very fundamental equation, so-called quantization condition or commutation relations, right? You should ask, what are this? What is the relation between those different conditions? So gauge fixing conditions, in some sense, is more priority than others. Okay， 就是比别的条件更优先。Why? Because this leads you to the correct degrees of freedom. Okay, it doesn't really matter classical or quantum. Okay? Just to get the correct degrees of freedom. Okay, so in principle, you should impose this. Or sometimes we call it gauge invariance for physical observers. They're the same thing. Right? We demand the gauge invariance is very prior compared with other conditions. Okay, even after quantize it or before you quantize. Okay, this is just to get the correct degrees of freedom. If you don't get the correct degrees of freedom, how do you mention to quantize? Okay. Okay, so. This is just some comments. So let's use it. Let's use this condition. Then it should simplify things a lot. You see, because this is the condition for somehow for free. You can use it. Okay. Continue your analysis for the equation motion. For example, the first. This equation plug into this first. Immediately simplify the equation, right? So under this equation. 1, 2, this is 3. Under this equation, 3 becomes, then 3 becomes partial j, where a0 equals to 0. You see? This is a pretty simple equation. You can see this derivative is only associated with the special coordinate. Okay, as I said, there's no time. Okay, there's no time involved in. Okay, so you should be familiar with this equation, right? Because this equation can be solved explicitly if you tell me the boundary conditions. See? Is that true? Yes. This is just the file. This is a familiar equation. So let's combine if we combine this equation with for all of boundary conditions. For all, I mean the field should decay at infinite far away. Okay. Then what will be the solution?
0.
Very good. Very good. Okay. Very good. We learned something maybe in your first year college physics, some unique theorem, right? Unique theorem. So in this case, A0 or B0. Okay. Okay. B0 or B0. Remember that in this case we're not coupled with matter yet. Okay. Or this just no matter system. Just a free photon system. Okay. Now, if you insist the boundary condition is 0, according to this equation, A0 should be 0. Then this saves you a lot of job because it just tells you this. You can throw it away. Okay? You trivialize this A0. A0 field under this particular boundary condition is entirely 0. You can forget this. Okay? This moment, you should forget it. So let's continue. We have 0, the second one, right? Second equation. So for second equation, again, let's try to take use of this fixing condition. Okay? Then this is 0. Okay? This is 0. So what I get is A0 is also 0. What I get is cos I equals to 0. Okay? Cos I equals 0. Okay? But you might say, okay, it's, through some effort you are now arriving at here, but this still looks like a 3 degrees of freedom system. You see? So this is the pocket Ki equals to 0. Okay? Then again here, as we always emphasize, you shouldn't forget the gauge fixing condition, because gauge fixing condition is like really a priori condition. You should take it all along your analysis, which means that even you look at this equation, you should understand it together with the gauge fixing condition. Okay, it's not quite independent one, but this will also be understood together with the gauge fixing condition. Okay, because this is always there. Okay, so this is the complete answer up to now. We have this. We have this. So let's look at this more carefully, and let's try to solve this equation. Right now we are here. Let's try to solve it. What is the solution for this equation? It's not a big deal. It's almost the scalar, free scalar equation, right? Apart from there are 3 indices, just 3 components. That's it. Okay. Same equation. Mathematically, is precisely the same as the box phi equals to 0. That's it. So there are 3 phi. Okay. So the equation can be solved. This equation can be solved. When you solve equation like before, get something like this. For example, this is the triangle solution for this equation. You give it like this is the solution. Okay, this is the solution. So why is right? This is the solution because box acts on this A, you plug in, then you get P squared. Okay, and P squared is 0 in this case because P0 is defined as alone the p vector. So this means p squared is 0. Okay. So this is the solution. Don't forget that this is itself, left-hand side is vector. Okay. The vector is not a scalar. The vector in the space. Okay. Then this coefficient should also be a vector. Okay. This coefficient should also be vector. Or in this case, epsilon. C vector. C vector depends on p. Depends on p. Is that okay? This is a p-dependent vector as a coefficient, right? Previously, we have some, when we solve phi, remember that? When we solve phi, we also have some coefficients, okay? A and A star. Are p-dependent A and A star, remember that? Eventually, you promote to the A dagger operator, right? You quantize. In this case, it's similar. But we want to use this vector to carry a very particular job. So as said, we shouldn't forget this equation. Then you should let this solution satisfy that equation. Okay, partial j a j should equal to 0. So this is my gauge fixing condition. It's important condition. So to satisfy that one, you can easily check the partial j equals to 0 is equivalent to a which vector thought p is 0. Okay? Exactly. So p is 0. So this means what? This means a simple relation between the momentum and this the p vector. Okay? It just means this vector and the p have to be orthogonal. So the inner product is 0. Inner product is 0. Okay. So we use this Xi. We use this Xi to explicitly specify where is my polarization. You see, this is my field is a vector field. Vector field means that at each space-time point, there is a polarization, there is a direction, right? This is a vector field. See? And according to these constraints, that the direction should be orthogonal to p. What is p? P is the motion direction of your wave. Okay? Is that clear? P is the motion direction. But for the vector field, there's another polarization condition, polarization direction. Okay? So in p space, you can see this condition transformed to p dot this Xi equal to 0, which means the polarization is essentially orthogonal to your motion direction. Is that clear? Is that okay? Right? You have some wave, but your wave has some kind of internal structure. There's some vector wave, okay? Then you also have a motion direction. The point is this result tells you that this direction is always orthogonal to this one. Now we're in three-dimensional space, okay? We're living in three-dimensional space, we clear? So whenever you specify your p direction in some way, the remaining orthogonal direction is a plane, right? Is that right? It's a transverse plane. Then you have two independent choices. Okay? There's two independent choices. Then you can consider this one is some linear combination of that two independent. Let's see 1 and 2. Okay. So essentially, from the observation here, we arrive at this result. Okay. Therefore, for each p, one can choose two independent orthonormal vectors. A1 and B, and this one used there is a linear combination. With a linear combination of that. And so we could write the mathematical equation in a more clear way. So usually we have to use the epsilon. Epsilon is better, simple. But that's the thing. Okay? Let's use this way of these two equations. So basically, the polarization vector, the two independent polarization vector. We want to write down this. It should also statistical code for each one. R labels R1 from 1 and 2, okay? From 1 to 2. And of course, each one is orthogonal to P. Among them, between them, epsilon R cross epsilon S equals to delta RS and that's RS equals to 1 and 2. Okay? 1 and 2. Which means these two epsilon are orthogonal. Okay? Orthogonal. So epsilon does the job to tell you where is the polarization. That's it. That's the only job. Epsilon. Okay. Okay. So this almost answered the question, right? This already answered the question we want to ask. Where is our question? Our question is why. Oh, here. Already answered. Now this question is answered. So there's only two choice of the polarization. This is also consistent fit with the Wegener's result. Wegener's result tells you, according to Wegener's classification, for each P, okay, there are how many choices you can have, or how many independent states you can have. Now, even before quantize this Maxwell field, you see that what is classical analysis, okay? Because this is associated to the counting degrees of freedom. It's not, you don't need to really quantize it. You can see it quite often, right? It's just degrees of freedom. Okay? You can see it. So this is consistent with the Wegener's result, or fit with, or verify the Wegener's result, because we do see from here for each P there are two independent polarizations. Okay, this corresponds to independent states for focus after quantize. Do you have any question about why system has only 2 degrees of freedom? Of course, you can try to choose another gauge. Okay, that's far from unique. You can try to do some other way. For example, you choose some other gauge and go through the analysis, but the final result should be the same. Okay. Okay. And this Coulomb gauge is convenient as you can see, it's some one-step gauge. Sometimes when you choose gauge fixed condition, you cannot finish one. You have to go step by step. Sometimes you fix it, you partially fix it, and then completely fix it. Okay, but that's a little weird. But in this case, it's a little, yeah, it's very clean. And yeah, in particular, as you can see, just down to the final, almost, as you can see, this solution is almost prepared for quantization. You see it? Right? Because this equation combined with this equation it just tells you there are two physical degrees of freedom, and all the modes are also very clear. So, okay, you only need one more step to quantize this field on the Coulomb gauge. Okay?
Although it's not using Lorentz gauge here.
You can do it, yes. It's a little complicated, but it will be equivalent. You can go there. You can go from Lorentz gauge. We'll discuss the Lorentz gauge.
The Coulomb gauge is convenient for quantization. And
Both you can do quantization. Well, convenient maybe it's up to you, which is convenient. But I think Coulomb gauge. Yeah, I think fairly speaking, each gauge has the advantage and also disadvantage. It's not fair to say which one is certainly better than the other. Yeah, we're going to discuss Lorentz gauge when we try to derive the photon property. Okay. For that purpose, it's convenient. Okay. That purpose is convenient. Okay. You can even think if you are really a deeper thinker. So you can ask a lot of questions here. So here I choose to present this gauge fixing condition in this form. See? Or in other words, as some constraint for A field. There are also some alternative way. For example, you can ask why now you write some equation. You might think it's similar to some equation of motion, okay? Or constraint, okay? But why don't you just change your Lagrange, for example? Right? Why you choose to change your equation for A? Is there any alternative way? Does this gauge fix? That's also a good question. You can try. Okay. You can try. For sure, you cannot do for F, right? Okay, because F has no ambiguity. Or for E and the B field, then it's that for B. But you might try to just deform your action, Lagrangian. There might exist a way to deform your Lagrangian is equivalent to gauge fixing. Okay. You see, Lagrangian is the function of the A field. We know A has ambiguity. Sometimes a little confusing. Last time we also mentioned the F variable looks more physical than A field. Then you might say, why don't we just forget about A? Why don't we just write everything in terms of F? Then we can avoid all this redundancy, no? Who said yes? Who said no? Can we do it that way?
But the ancient identity is an extra constraint.
Yeah, but blank identity is for F. That's fine. What I'm saying, can we just abandon, throw away the A variable, just use everything in terms of F? Can you do that? Or what is the payment if you do that? Anybody has answer? The point is the A itself is not completely unphysical, okay? Why? Because there's a famous phenomenon you should learn from your quantum mechanics. What is that? A is important. What is this?
AB.
That's right. There's a Harrow-Bomb effect, okay? Okay? The Harrow-Bomb effect. We see that A has a physical effect, okay? You cannot completely forget about A. What we're discussing here is just say A has A has some ambiguity, okay? It doesn't mean A is completely unphysical, okay? Okay, A just has some gauge redundancy. A is equivalent to some other a little bit of shift of A. That's that's it. Okay. We're not saying that A is completely unphysical. You can throw it away. Okay. For example, if you can construct out of A, make some object satisfy this gauge invariant, then this is completely physical. Okay. You see what I'm saying? For example, you can do a loop integral of A. Okay. We will say this is a famous physical object called a Wilson loop. Okay. You can do a loop integral A, then this is completely physical object. Okay. Yeah. So we finished that. So before we go to quantization, let's mention that's even in the classic level, since we already mentioned this gauge symmetry or gauge redundancy. Continue to do fast. A little bit more about this gauge transformation. So gauge transformation, gauge transformation is sometimes also called local transformation. Okay, local. Should I say yeah, it's local transformation. And this is manifest when we consider couple matter with the photon. If we include okay. So let's try to include matter. So far, the analysis we didn't include matter. We didn't include the charge in matter. Okay. Now let's try to include it. Another way to understand the gauge invariance or gauge transformation is try to promoting this a global symmetry we learned before. Okay, when we learned Löder's theorem. Okay, when we learned Löder's theorem, there's a famous example called complex scalar field. Complex scalar field is invariant under U1 rotation. Remember that? It's a very simple example, right? Then you can try to promote that U1 rotation to some local transformation. Local means space-time dependent. Okay? Okay? Then you realize that under local transformations, a very complex scalar itself is not really invariant. It's not invariant. Okay? But you can try to make it invariant to couple with photon. Okay? Okay? So this is so-called demanding the gauge invariance to develop the coupling between matter and photon. Okay? Okay? Or promoting the usual global U1 symmetry to some local symmetry. This is quite related to the gauge invariance, right? This is also related to this Professor Seng Yang's work. Okay, what he did is just generalize this Maxwell's equation to a matrix variables. Okay. There's a very, very interesting story. I suggested to go to the history to see how did they find their equation of motion for Yang-Mills field. Okay. Actually, their motivation is very, very very, very, can say, at that time, yeah, it's, how can I say, the original motivation for Yang and Mills trying to develop their equation motion is just to generalize the Maxwell equation to a matrix variable. Now, when we write down Maxwell's equation, all the single variable is just a function. You see, it's not a matrix value. You see, it's not a matrix value. No matter A or this E or this B, okay, or this B. But they want to try to generalize to the matrix value, okay. By matrix value, I don't mean this A mu. For example, mu has the mu has the A mu, then A has a mu index, then looks like a vector. I don't mean that structure. I really mean the each component there's a matrix value. Okay. Then they try to make the equation consistent. Then they invent or discover the Yang-Mills equation motion. It's a very interesting story. Okay. So what we have is how to matter, how to understand the equation invariance from a different perspective. Before our stuff, when we learned the complex, free complex scalar field. For example, for the Lagrangian partial mu pi star, if you still remember, minus m squared pi star phi. This is the free action for the complex field we learned before, okay? And famously, this is the invariant. Under the U1 transform U1 rotation. For example, you rotate phi x. You rotate phi x to e to the minus I alpha phi x. It's easy to check. This is the invariant. You see. Now, previously, we focused this alpha is a number. Okay, it's a number. It's not a function. Meaning what?
Global X.
That's right. This is the global transformation. Global in the sense for all the different x. Okay, this means for all the different x. X means space-time position. For all the different x, there's a phi field, but they rotate uniformly. Okay, everywhere the same. You see? See? All the phi, no matter which different x, they are just rotate uniformly because this is the constant. This is the constant. Now, what if we instead consider some local rotation? For example, I want to consider a little bit generalized from here. For example, minus I alpha, but alpha instead of a number now is a function. Now alpha is a function of x. Then rotating this. What if we do this? Okay. In particular, of course, I want to construct a theory which is invariant under this. Then what should we do? That's the question. Okay. This is so-called using the local transformation or demanding this local transformation invariance. Right? Or this actually there's a famous name, another name for this. This is so-called gauging. Okay. When you promote global transformation to local transformation, there demand the theory is invariant. Okay. This is the so-called demanding gauge invariance to develop your theory, okay? To construct the theory. So how to construct this one? Of course, if we don't know QED, for example, if we don't know QED, you have to do it step by step, okay? You have to do it step by step. You have to find different terms. What are the possible choices? They are invariant under this transformation. Of course, the first examination you should do is for the partial phi squared term, okay? This is kinetic term. So now, but compared with kinetic term, this term is pretty much easy. You can verify the so-called mass term. If you consider m squared phi star phi, you can easily check and tell this term is fine, okay? Even under this local transformation, this is invariant. You see? There's no derivative, right? There are only two factors, and this is conjugated with this one. Then that exponential factor will cancel. Doesn't matter if it's a number or it's a function. So this term is fine, or invariant. However, this is not true. This is not true for the kinetic term, partial term, as you can see. You can easily check yourself. You plug in this transformation. If you plug in this transformation into this one, don't change anything else. For the same term, it's not invariant because this is derivative. This is derivative. So how to solve this issue? The way to solve this one is this is always the trick we do in field theory. Okay, whenever you see something is not quite invariant, or there are some remaining terms you want to clear, or you want to compensate, the easiest way is to introduce another field. Okay? Okay? Right? That's always the trick. Easy to introduce another field. We do the same here. We can introduce another field, so-called gauge field. Okay. This gauge field is nothing but the Maxwell field. Okay. And we let this gauge field also transform. Okay. Also transform. Okay. Also transform in this way. It's the same transformation we learned last time, right? It's nothing but the gauge transformation, which preserves this Maxwell theory. Okay. Now we ask more. We want to couple this photon field to matter. I want to let everything elegantly. They are invariant. Putting together, they are invariant. Okay. And we know this A transforming this way. Now we can consider. Now we can consider something called the covariant derivative, because we want to make this d or partial phi squared term. It's really invariant. Then we can improve this Euro derivative to something called covariant. Covariant derivative. What is that? Let's use the capital D to denote my covariant derivative. Okay, partial D is the before. This D mu defined in this way. This is equal to partial mu plus I A mu. Okay. So previously we have this as my derivative, this is normal derivative. And now I include another piece which is IA. I define another, so something called a covariant derivative. Okay. Then you can easily check. It's not difficult. It's pretty easy exercise. You can check. This covariant derivative acts on phi, which is by the definition is the partial mu plus IA mu acts on phi. Under this transformation, under which transformation? Under under the transformation here, under the star transformation, the star transformation is two pieces. You now introduce another field. You let this another field transform accordingly, okay? Simultaneously, okay? Accordingly together with that transformation. Two object transform, okay? Then under those transformations, the star transformation, this one will transform very elegantly because this is, yeah, you can see this becomes partial star. Yeah. Which means that this object now transforming now only up to a face. See, only up to a face. Now then, if you put these two of such objects with this one with his conjugate partner, okay, put them together, then this face cancels, right? So this essentially means the E mu phi star. E mu phi is invariant. Under star. So we find the improved form. So this is the improvement. You should define a new derivative called a coordinate derivative to replace the original derivative. Then it's done, okay? And also, of course, demanding A also transform accordingly. Then you get the invariant object. Now you put everything together. You put everything together. You found this one, then you put everything together. Now don't forget that Maxwell theory is already invariant under this one, okay? Right? And the M squared phi star is also invariant under this local transformation. Now we found this kind of coupling, okay? This kind of coupling or improved derivative square term is also invariant. Then there are three terms are invariant, okay? Three terms are invariant under the gauge transformation. Then we can put everything together. The theory will be invariant. So this said that there is a theory. There's a theory of the invariant, okay? A theory is the case of invariant. And this gauge invariant theory is sometimes also called QED, scalar QED, because we added the charging matter, okay? QED is the quantum dynamics, okay? The point is this term is actually include this coupling between A and phi, okay? Because there's a charged matter, you can easily ask the question how the charged matter couple with photon. Okay? If you treat the photon, if you think photon is the gauge field, then there's a charged matter. You should ask the couple. The coupling is included here. Let's count which type of coupling it has. Okay, let's count it. So if you put these two terms together, okay, if you put these two terms together, which means you have this one with its conjugate pair, right? With its conjugate pair, and then you multiply these two, okay? You see? Then you will have right. There's another factor u minus I is conjugate. and bar. This another the term like this. This term multiply with this one, then it's counted. Certainly there is a coupling. There's a coupling between a partial mu phi and a mu phi star. You see, right? So this is like a phi star A coupling, okay? Together with the partial mu. There's also the A phi star. There's two A, okay? There's A phi star coupling. You see? So there are two different coupling terms. Even though this looks very simple, it's just a simple form, but it includes two types of coupling. One is there's only one A, but there are two A in the other 4-point coupling. A phi star. So this is called a scalar QED. Later, maybe in the end of today's lecture, we're going to introduce the spinner if we have time. So after we introduce the spinner, we can replace this scalar by spinner. There's also a similar spinner QED. That's more close to our real world. This is our real world electron with spinner. Okay, with spin half. So this is just a toy model. This is just a toy model to discuss the charged matter with photon. Now we said that we can somehow promote a global symmetry to two gauge invariance. You see, you can also go back. Okay, you can also go back. See, if I know I do have a gauge invariant theory, or I do know my theory is invariant on the gauge transformation, then it implies a global symmetry. You see? You see it? Even though they are quite different things. Okay? Logically, the gauge symmetry, if you want, gauge invariance and global symmetry is not who includes who. It's not this logical relation is not like this. They are just totally different things. Okay? If one is local, another is global. Okay? Okay? You cannot say local include global. It's not true. Because global is global. Local is local. They are different. Okay? But indeed, whenever you observe, whenever you know you have a gauge symmetry, it implies global symmetry. It implies something different, but it's right. But it's related. Okay. So we call gauge symmetry implied. This is true. Implies global symmetry. How to imply? It's simple, right? You just turn all the function alpha as a function of x just to tend to a constant. That's it, right? It's very cheap, very cheap. So if this is true, then what about Noether's current, right? Immediately remind us we should work out Noether's current if there is a global symmetry, okay? Noether's current. So let's work it out for the scalar QED. Okay. We know scalar QED already. The theory was constructed there. Now you can easily check yourself. Scalar QED has a global symmetry also. Okay. is just the traditional UI rotation. And you treat all the alpha instead of a function, but now it's a constant. Okay. Now, since alpha is a constant, so A transformed in the way that A shifted by partial alpha, right? So if alpha is a constant, then partial alpha is what? It's 0, right? This essentially means A does not transform. Okay. Only the charged matter or charged scalar transform under a global phase rotation. This is what we call the global symmetry for this scalar QED. There's also a global symmetry. And since this is a global symmetry, if there is a physical consequence, which is another current, right? So we learned in the second lecture. So we should try to work it out. In order to work it out, or in order to test whether that current is conserved eventually, we have to use the equation of motion. In this case, equation of motion for phi and the phi star will be slightly different than previous equation of motion. I mean, without the gauge field case. Now there is a gauge field, okay? Suppose we turn all the electronic coupling explicit, then the equation of motion now becomes this one. So equation of motion was also improved because of coupling with A. You see, previously A is not there, so all the right hand side is 0, right? Now there is a A field because A coupled with phi. So a priori you should recheck everything. Okay, when this gauge field appears, right? Because as we verified before, to prove the conservation of the Nernst current, we have to use the equation of motion. But now equation of motion was changed. You have to recheck it again. So these are the new equation of motion. They are all A fields here. And since this U1 global U1 symmetry preserved the L, okay, so the current becomes simple, right? In general, it's up to total derivative. Then you have two terms, right? Remember that? Now it preserves L. It preserves the Lagrangian. So the current has only a single term. If you have many fields, then the current is simply given by this one. Right? The formula for Lagrange current. Then now we have two independent phi star fields. Just plug in and work it out. Right. Because we also know in this case, under the U1 phase rotation, this two fields of variation with respect to alpha is this form. Then you plug in here. Then what you get is slightly different again, compared with this no gauge field case. You get additional term, which is this one, because of the coupling of the field. Okay. It's different by this time. This is neutral current. Previously we have this one, now additional term. And you can check it's still conserved. Okay, using this new equation motion. Now there's an interesting observation. This J, the particular form for J, then you realize that this J is nothing but the part which couple with the A field in the Lagrangian. Okay? In your previously in the Lagrangian, you didn't write it literally, but you can do it. There's two types of coupling with that. There's a partial mu phi, A mu phi star, partial mu phi star, A mu phi. Okay. There's also A mu phi, A mu phi star. Okay. That kind of coupling. But whatever it is, you can try to write this Lagrangian that coupling terms in terms of let's say the J mu A mu term. Okay. Okay. If you factorize A mu, then you there's some J mu, okay, left over in that Lagrangian. Okay. Then you realize that this J mu is nothing but this J mu. Interesting. Okay. This is very interesting. This means what? This means that couple gauge field with charged matter, I can always treat as A mu J mu coupling. Okay. Okay. Provided that J mu is actually the laser current. This fact beautifully connect the conservation of Lerder's current and the consistency equation for the Maxwell field, okay, or Maxwell's action. See what I mean? Because what we're trying to say is this. I can simply, suppose I want to couple my gauge field with requires metal. I can simply just write maybe this minus. I can simply write my Maxwell's equation together with a J mu A mu couple. Mu is A mu. Okay. And then, what is the equation motion? Let's just at this moment just try to look at this one. Suppose I only care my gauge field and the charged matter coupled with my gauge field. I don't care anything else. The others will not be seen. Okay. And I'm trying to focus on the equation motion for the gauge field. Then, what is the equation motion? You try to figure it out. Without this J source, equation motion is here, right? You see? This is the equation motion, right? Now with this source, you will get the partial mu F mu nu equals to what? Equals to J. You see? Equals to J. Then you can easily check from that equation already for consistency of this Maxwell's equation with the source. J mu has to be conserved. You see? You see? Right? Because you have partial mu F mu nu equals to J mu. You see? Let's try to check it. Okay? This is a beautiful connection. From here, can you see the The J has to be conserved for consistency. You check it. Why? Let's take a partial nu. Okay, both sides. Okay, from the left hand side, partial nu, that's mu nu. What is this? What is this? This is 0. Okay, why? Because you can freely change the order of the derivative. Okay, there's 2 derivatives, but f mu nu is anti-symmetric. When you switch f mu nu, it's anti-symmetric. This has to be 0. So right hand side has to be 0. Okay? So consistency equation for Maxwell field becomes the conservation for the largest current. Okay. Although we can get this result from a very different way. But they match or they consistent. And maybe we can have a break and then we'll continue to discuss the conversation.
这个无数人形成的，这个是叶多。
哦，天呐，也太好看了。
哦，
带有大
因为那边是那那个，那也像，电池这么高的还，哦对的，做一个哦，后面的，他可以，他说把移动怎么啊？他说要想说你们今天早上给他体验那个你说有就是这个，这一上啊，应该是很难，对，因为这个啊，这是你的变 global 买 global 的变换呀，对啊，这个就是里面都这个说的是 global 的保密分的那个偏方嘛。那你说那边是用100直接放表出来的话，那这像是活的那种。哦，你这啥？不是，这就这个啥？这因为就是这个是吧？啊，对啊，这边是这个，这边是这个，这个和这个还差一下那个。你说没有饭？对，饭是一个饭单没有。显卡有点是吧？但我觉得你把这个 J 丢进来的话，那应该是把这个整个给填上，是吧？啊，还有个CPU是在15年。对发的2是在1点写的 AMD 的，这个对，那我们英特尔上对。上的这个要求应该是这几个有对，或者不是4507那显卡可以多嘛？来这个然后CPU 他说1万，这笔的话能写在任何资源。它就4500就是那个4500啊，就是这个。这个呢，你们找的是他这个是问题，他有那里看叫这个里面，这个是就是把这个这个啊，对，价钱地方他那个这个手机，这个对啊，你这个呀， 啊，
像有这个等于这个的话，
去北京是吧？
这边应该至少把派应该去排的一些。
真是北京干嘛？
这个又不是一，
对，我也是。这里是应该都少一点，有。哦，它定义应该是
就是一方面。
就是IE，
IE，
他应该加那个
IE，
对
，IE，他没有写，不然这个 E 对吧？
对，
这他妈 P 选太我又写。
那这一项对吧？往里放的时候，肯定不能直接写那样，就那个什么。
量级考虑。
你其实你忘了，你记得什么？
我录就是配了多少？那一定二三吧，对，很清楚的。我懒得把它推进去，懒得睡觉，它放在外面。睡觉也是懒得睡觉，外面我把这个抽屉抽出来，放进去。我就说反正就到我好几点，不想睡觉，到睡觉。
就是你像我写不像考人，
这边有一个美国人啊，
小红
给我也是。我在面前只能是会
很避讳。
就是刚刚你写大地的话，就没有看到没有这个，这个地方含的那个啊，大脑就是放了个提示，他们是那个他说然后再别说，他就是不懂，他是他可能是说大，因为比较大，就是他们的啊。还会认识他，认识他是那个好人那个带给这个你那个故事，带给这个现实上产生出来的。因为这里可以问就是他这儿结局里去，关于最近的相哦，那这个时候我认为结局是 source， 就是你认为结局是 source， 我那个结局是光，那个是也不是，因为当你在推这个不可能一种事儿，但是 JU 可能不是这，当他在 scan 的时候不是，正常的对吧？
啊，就是说我跟这个都是和他，
对，直接在拉斯干里面引入 JU， 认为 JU 不是，啊 JU 呢？你可以做点这种玩意儿，把差的慢下来，那你看你是选定就是 organization
所以说就把那个在第一就写成这种形式，所有双语关系。 那里面那个就是哪个形式？对，就是这个它里面是唯一的这个这个中有点就说这个可以对，因为你对这个动力它在这里有很多有人们所以说相对的任务的那个这个对方方面对方说是变动这里就我就你的电力就不会这里，我电问题不用你讲。
这样不单讲，这样意思的真因比没的，不是，那里只有一次个值，前面那个因为也少写了一个，前面不用，前面没有 A 啊。E 和 A 是绑定啊，对 ，E 和这边出现 A， 我觉得也有用，就它相当于说我把 A 的正负写出来，你只用 A 就是 A， 但是你加个 E 的话，就相当于把 A 提了个正负。哦，这个东西应该是，所以这相当于代币对，相当于跟 E 才是对，那这个 E 我相当于是把那个 A 提了个那就是说有一个 A B， 有一次 A B 就需要有一次 B。这边应该，这边我觉得应该再加个 E， 比较少，要加个 E。准确的判断，这个意思正那个什么，那你想提什么都这个性质本身就是一个，人家那个，因为你要和一般正常的电子才变得可歪曲。可能它会更加哦，这里艺术符形式，要不速度它的系数，对，这样理解，让它市场可以发展。做的也很吃力。你看啊，一体计算的时候，不是经常这样一直给了一个手的，就是我第一人战斗完不要传，但是我就是知道啊。可能就是反正吧，接受这个问题就还好熊大形象比较好。在这里练习，这里讲真有。还有个问题，就是如果A 这个 E 的话，相当于同一个跟前面加
我一直考很多的，Invariance copy strength， 一个大小，因为调一个偶合的时候，可以调一个，
反正是不是就是有一个 A
有一个 A，right，如果有两个 A 就是一直不了。
如果我们相信那个因为上来怎么第一个月给的。 这没有是不是因为但是就是有一个这生活应该有一个，对那边这其实应该还有一个压力。在高兴这个都尝试这种前置到你这个倒是这个东西，那就是放上一个模型，然后
Okay. Let's continue. So during the break, someone asked me how to get this equation. And the key is to get this equation. You should view J is independent. Okay. At this moment, we don't care how to realize this J, whether it's a scalar charge matter or fermatic or whatever. Okay. I don't care. Okay. I just improve the original analogy by adding a mu J mu. Okay. And treat J mu as some general current source, a source current. And J mu is independent of the others. It's just independent source. Then you can easily get it. Right? The point is, for the left-hand side to be consistent, this has to be conserved. J mu has to be conserved. Okay? And now, once you write down the explicit realization of J mu, for example, you figure out, now I'm talking about the charged scalar field. Okay? When you write the explicit realization, then you can check consistency. Now the conservation equation here becomes the conservation of Noether's current from here. Okay? Before the realization, you don't know, right? You don't know the realization. You don't know the elementary field realization of this J mu. Then you don't know Noether's theorem, right? You only have consistency. But the point is, these both are consistent. This consistent condition consistent with this Noether's conservation. Okay. So later we will find another realization, maybe not today, but later using the electron or fermion or spinor, okay, to form another J mu. So this is the discussion so far. This is the discussion about how to add a method or couple the heat field with the matter. And we have to finish the quantization, the photon. So in order to easily understand the quantization of the photon, the first exercise, let's say we're going to talk about the quantization. Before the photon quantization, so far we only know about the quantization for free real scalar field, right? Right? And we know the quantization to some extent to the interacting scalar field, real scalar field, okay? Like the 5 cubic or 5 quadratic interaction. But we don't know somehow much about this type, which belongs to the category of multiple degrees of freedom. Right? Multiple degrees of freedom, which according to Wigner's classification, this might carry some higher spin, right? Not spin 0, spin 1, for example, photon spin 1. Now in this case, there are multiple degrees of freedom. Okay, not a single degrees of freedom. So how to quantize multiple degrees of freedom? Like a mu. But before this, actually, we have another typical example, which is phi star itself. Okay, the complex scalar field itself also has multiple degrees of freedom. You see, because in this case, you can write it as phi 1, phi 2. You see, it's up to you. You can choose to take a variable phi star. You can also take a variable phi 1, phi 2. Right? Because phi equals to phi 1 plus I phi 2. Okay, it's up to you. They're the same thing. Now, if you choose to think about it this way, phi 1, phi 2, then there are two real degrees of freedom for the complex field. When you quantize it, you should organize the real scalar quantization into a little more complicated form, right? But it's actually the same thing, just organize it. So let's first consider the simplest complex scalar. With the complex scalar. So quantize complex scalar is nothing but do twice quantization, or not twice, but do the quantization for two real degrees of freedom. So let's try phi 1. This is our linear equation. We quantize it. Let's say we have AP minus IPX plus AP diagram plus IPX. Okay. Now, since I have an additional index 1, we will have another index 2. So let's put a 1 here. So this is 1. Now we will also have 2. So this will be AP2. This will be the AP diagram 2. Right?
sorry 背跟黑板倒。
Yeah. Right? Nothing but when you do for the two real fields, real scalar, right? The familiar equation. Now you can organize this one. Let's say you can think about the complex scalar field. You can define it in this way. You just have two components, phi 1, phi 2, right? It's up to you. The structure, how to organize it, up to you. I can choose to organize this in this way. Then this will become, let's rewrite it again. This will become J equals to 1 to 2 epsilon J A P J plus epsilon J A E J higher. I can organize it this way. It's just trivial, okay? I show this example just let you get familiar with this additional structure, include this so-called polarization vector. Okay. You can formally think the complex field in this way, phi 1, phi 2. You can formally think that this is a two-component vector. Okay. Two-component vector. Then in order to quantize such kind of object, looks like a vector in the field space. Looks like a vector. Then you should introduce some additional structure apart from all the familiar structure. This is all the familiar structure, which is AP e to the minus IPX, right? AP diagram into the IPX. So in order to complex this structure, I have to introduce an additional vector. It's called the epsilon. And of course, additional index J. Now, since there are only two components, 1 to 2, the J only runs from 1 to 2. Okay. It's just a trivial organization. Now in this case, epsilon 1 is 1, 0. Okay, epsilon 2 is 0, 1. As you can check. Okay, this is completely equivalent to two equations. Okay, see, it's just equivalent. I just merge. I just want to organize these two equations into a single vector equation, and introduce small additional structure to capture this. This is a vector. Okay. Okay. Because when you quantize a vector, you should get a vector. Okay. If you don't introduce such kind of epsilon, then you don't have the vector. Okay. That's weird. Right? When you quantize a vector, you should get a vector. So epsilon does the job. But you shouldn't be scared about this epsilon. Epsilon is just did this job. No, nothing else. Okay, nothing else. Nothing. Then, if you understand this one, then for the Maxwell field quantization, it's pretty simple. It's very simple. You can just one line. By one line, you write down the result. Okay. Here. Now we are ready to quantize Maxwell's field, because Maxwell's field is, we know it also has two physical degrees of freedom, and in particular, from the previous classical field study. From the previous study, we already cleared all other redundancy down to the Maxwell field under Coulomb gauge in this way. See, this is the only remaining degrees of freedom. Okay, together with the Coulomb gauge fixing condition. Okay, this is what we have. Now you can immediately write down the quantization of this one. And as we already saw previously in the classical solution for the equation of motion, there are two independent polarization vectors, okay, labeled by the RS index. So you can write this way, okay? But compare with this scalar case, the scalar case is trivial, right? This two polarization is just given in this way. It's trivial. But in the case of vectors cases, it's a little complicated. This epsilon polarization vector really depends on the momentum. Okay? Because your momentum can change, okay? But for different momentum, the polarization will accordingly change. Okay? So in principle, epsilon is a function of P. Okay? It's a vector function of P. It's not something given once and for all. It's not. Okay? It's a little complicated, but it's not a big deal. Okay? You can solve it. It's a concrete function. Okay? It's a concrete function whenever you know P. Now all the remaining is trivial. Okay? All the remaining is trivial in the sense these are just usual AP in the AP diagram. Every additional index, small r, because the small r is equal to this index, small r. Okay. No more than this, okay? And of course, epsilon polarization vector satisfy the condition or constraints as we saw before. The same as there, okay? Same. This defines the epsilon as a polarization vector. This defines the action as a polarization. And the remaining structure is the same scalar case. Now you can ask, what about this is the quantization for A, what about the conjugate variable? What about the conjugate variable? Then the first question you should ask is, what is the conjugate variable for A? What is the conjugate variable for A? You should derive it from, you should calculate it from Lagrange. How to calculate it? The conjugate variable usually we denote by pi. This is, in this case, is AI, right? It's only a 3 vector. So the pi I, and the pi I, you have to calculate it from the Lagrange. You take a derivative with AI dot. Remember that? Right? So what do you get if you do this calculation? This is the minus f0I. And what is that? This is ER. This is ER. So the conjugate variable for A is E. E is like electric field. Okay? It's E. And we can also write that we can also write the quantization for E, right? As we do in the scalar case. In the scalar case, we have phi and pi, right? So phi and pi. So the quantization for E is similar. There is a minus pi in front. There is omega p over 2, like a scalar case. There is also a polarization vector. And the remaining thing is the AA dagger. For E, okay? For E, and there's also commutation relations. There's all quantization conditions. Which is the AP, AQ. There are 2 additional index below the polarization. Because all these have carried an additional index, RS. So this equals to AP. Dagger mu is AQ. That's dagger equals to 0. And non-trivial commutation relation comes from AP plus AQ as dagger. This is equal to 20. As before, a delta RS multiplied with 3-dimensional delta function. Okay, everything is standard in terms of A diagram. But there's a slightly non-trivial commutation relation is you should check yourself. Is what if you write in terms of this AE field, right? The AE are conjugated with each other. Previously, we learned that it's like XP, right? The phi pi conjugation should satisfy the standard commutation relation. Remember that? Maybe given by delta function, equal time commutator, right? But in this case, it's not quite true. The right-hand side is not quite just the delta function. Okay. What I'm saying is, if you try to derive the AE commutation relation from this A dagger here, you arrived at something look different compared with scalar gates. Okay? Essentially because of the gauge fixing condition, or this gauge invariance, gauge fixing condition. Because here we work everything under the Coulomb gauge. We work everything under Coulomb gauge. You can check the naive commutation relation between A and E does not satisfy AE. We have to improve the right-hand side from the delta function to some little complicated. So that's something very interesting. You should check yourself. I'm going to escape it. So okay, let me read the question here. What about the AE relation? Commutation relation. Okay. What about this? So next, we want to briefly discuss another gauge choice. As someone asked, what if you choose the Lorentz gauge? So interestingly, I'm not sure everybody knows this story. This Lorentz is quite that Lorentz. You know, there are two different Lorentz, but many textbooks mixed up. Okay, maybe for example, Paskin. I'm not sure. Paskin mixed it up. These two are two different persons. Okay. It's not the Lorentz for Lorentz transformation, okay? It's another Lorentz. But many, it's a confusing history. Many people, a lot of people confused these two persons. They think it is the same person, but it's not true. Let's briefly mention. Sometimes we go to the Lorentz, as you can see. The other Lorentz, there's a T. Okay. What is Lorentz gauge? Well, as said, since A has some ambiguity, why don't you just put the constraint about on A? In the Coulomb gauge choice, we just say partial J equals to 0 using this condition. But what if we employ some other condition? So Lorentz gauge is another condition. It's usually present in this form. Okay. As you can see here, instead of J index, now I use mu index. Okay. So this manifestly preserves Lorentz environment. The previous Coulomb gauge unfortunately doesn't. Okay. You see? Because the gauge condition itself is not Lorentz environment, but in this case it is. The condition itself has contracted over mu indices, which means the condition itself is Lorentz environment. See? So this condition is preferred if you want to preserve Lorentz environments. See, manifest. Then next question is how to use it, right? How to impose it. One way to do it, like what we did before, is to do the order style analysis step by step. And keep in mind, always keep in mind, there is a God-given condition, a priori condition here. together with this condition, then you derive what you want. That's one way. A slightly different way is, as mentioned before, we can try to improve the Lagrange. Okay. We can try to improve the Lagrange from the very beginning. This is sometimes called the covariant gauge. Well, there are a lot of different names, but yeah, as you continue to study, you will see many different gauges. And this is the Lorentz gauge. There's something called a covariant gauge. Covariant gauge. Okay. What do we do for this to employ this gauge? It says that instead of put some constraint like this, we can try to deform the theory. If I deform my Maxwell theory in this way and introduce an additional parameter, C. You can, yeah, sometimes this is a little confusing, how to understand this covariant gauges, but why do we choose to do it this way? Yeah, there are a few remarks. First of all, still it preserves Lorentz invariance is quite clear, right? It preserves Lorentz invariance. This is one big motivation. Another thing you can see, deform the theory in this way preserve all other conditions, right? We introduced quite a few important conditions, like before how to construct a good theory, like locality, right? Like locality, energy should bound from below, blah blah blah, things like that. I know, right? Of course, the Lorentz invariant is also important. Right? So you can see this term preserves all others, except for the gauge invariance. You see it? Yes. There are all others except for the gauge invariance. Yeah. So this kind of deformation is a very natural choice. It's a very natural choice. And later, when we learn the path integral, we will get some more deep understanding how to understand this deformation. For example, you can treat this parameter instead of parameter, but you can also treat this as an auxiliary field. Okay, 辅助 auxiliary field. If you treat this object as an auxiliary field, you should integrate out. The integrate out this auxiliary field is essentially equivalent to impose. This is the same thing. So in that sense, this is also a natural choice. But at this moment, we don't go that far. We just treat this as a deformation to my original theory with some parameter. Okay. Okay. But keep in mind why this is the choice. Why don't just really write something else? Okay. Right. It's not just some accident, but there is some reasons why we choose this to break the gauge invariance in this way. We know gauge fixing is essentially break gauge invariance, right? Right? Why? Because we draw some systematic picture, even though this is systematic, but it's very useful. Okay. Gauge invariance means you keep all this gauge orbit, right? Right? It's just redundant for staying in different points. So now you gauge fixing means you lose this ambiguity or gauge redundancy, right? Or in other words, you break gauge, not break gauge invariance, but you kill this gauge redundancy. Okay, you kill this gauge redundancy. So you can check with this term. You no longer have this gauge redundancy like before. When you shift a by total derivative, right? This term is not involved. You see. So there is a function of this term to do the gauge fix. Right? These are remarks. This is useful. This is useful. Why we want to introduce this one? This is useful in a sense. Mathematically, it solves some problem for this Lagrange. Okay. Okay. What is that problem? The problem is as follows. For this Lagrangian, if you want to write this as the A box A, okay, like what we did before. For the scalar case, if you write it as the phi box phi, then you take an inverse of this box, you get a propagating. Remember that? That's the case for the scalar case. Now you might say, okay, let's do the same thing in order to work out the photon propagator. But the point is, when you do the same thing without this term, only for this part, the operator for this A field here does not have inverse. Okay, the inverse does not exist. Okay? You can prove it. So in order to find an inverse, if the inverse does not exist, you cannot work it. In order to find the inverse, we choose to first deform it. Now the point is, this whole thing do have an inverse, okay, for this box operator. Okay. That's another crucial reason why I want to introduce this. Okay, so let me do this a little bit more explicitly. Now with this improved term, the equation of motion for a nu now become box. This box is really a box. It becomes a box A nu plus I 1 minus 1 over d pressure nu pressure nu. You can easily check, right? Why? You have raised my Maxwell equation? No, I don't. Here. So this equation is precisely that equation without this epsilon term. Okay, you see? Now we add this Cassi. We add this Cassi term. This Cassi term only carries the partial A squared. Okay, so it only includes this partial A term. You just contribute to this way. So this is the new equation motion with this. Now you can check from this new equation motion. Indeed, there is a nice inverse for that quadratic operator, or the operator between A. Okay. Let's check. So one can check. Now, okay, good. Now let's write in P space. In P space, this is nothing but the minus P squared G mu nu plus 1 minus C P nu over P squared. Yeah, it's simple. There remains the analysis, right? Yes. Okay. So in momentum space, the operator in the equation motion is okay. You see, I just replace the derivative by using P. This one, and you can check the inverse of this operator. Inverse of this bracket operator is minus G mu nu plus the C minus G mu divided by P squared over p squared. Okay? You can check it yourself. It's not difficult, it's super easy. You can check this multiply this operator, you get 1. Okay? You get 1. You check it, it's not so difficult. Right?
The minus sign on the mu of the
Yeah, minus sign. You can check this, this you multiply this with this one, you get 1. Almost a trivial exercise. Now, when you have this one, then learn from the Feynman propagator for scalar field. We should treat this inverse operator seriously, okay? Because that's what we want. The inverse of some box, okay, is with this I epsilon deformation is the time ordered Feynman propagator for that field. Okay. So we can do also in this way. This essentially means that we can get the photon, time ordered photon propagator very easily. So we're ready to write down the photon propagator with this one I epsilon prescription. Of course, we haven't yet classified this very carefully. You can do it yourself. In the case of Feynman propagator for scalar field, we just have everything in great detail, right? Why I epsilon is responding to the time ordering, why the contour, how to classify different contours for that integral. But in this case, we just list the result. So the photon propagator which is the, this is a free field, which is the time ordered. Time ordered 2-point function plus A working for different values. This is nothing but we have I, we have a condition I. And all the remaining part is nothing but the inverse of it. Okay. The only thing we did a little improvement here is the I epsilon. We skip the proof. With I epsilon works precisely the same way as before. With this I epsilon, we can claim we get the time order. That one is just that one, okay? And we multiply I, okay? Like what we did for scalar case. For scalar case, remember the momentum space Feynman rule, okay? Is I over p squared minus m squared, okay? Plus I epsilon. The same thing here. So final comment is that what is the relation? You mentioned a different gauge, but what's the relation? The relation is sometimes within this covariant gauge, as you can see, you can choose different values for this Cassi. Okay. So for different values of this Cassi, we also for these different gauge. Okay. So when you choose a thing, for example, this is 1, we call this is the Feynman gauge. Maybe it's just due to who used it first. You put the length. And when we use this c equals to 0, we call this is a Lorentz gauge. Okay. So it's related to Lorentz gauge. Okay. And you can check. You can check why Lorentz gauge should be consistent with this condition, right? You see? You can check this is consistent with that. Can you see some from somewhere? Some equations? For instance, you can check a photon propagator. You see? When you set c equals to 0 in the photon propagator, that propagator or two-point function perfectly consistent with this condition. Why? You see this? Why? Because when c equals 0, right? You see, when c equals to 0, you try to act partial mu here from here, okay? If you try to act partial mu from here, you try to act partial mu, then you can check this is 0. This is automatically 0, always 0, okay? It's always 0. This is always there, right? Because p mu, upper index p mu here, you get the lower p mu. This is 0. With the upper p mu, you get a p square. P square cancel with this p square. Okay? Then you get a lower index p mu, which precisely cancel with this p mu. Okay? So the bracket, when you act on upper p mu on the bracket, you always get 0. Okay? So that's nothing but the condition here. You see? Right? Another way to see from the Lagrange is that when c equals to 0, you have to impose this is 0. Otherwise, your action is blows up. Okay? When you take it seriously, c goes to 0. If you don't impose any additional condition for this factor, your Lagrange becomes infinity, okay? Blows up, it's sick. Okay? We don't want that kind of thing in physics system. Okay. We have to impose that in the same. This is another way to see the symmetry. Okay, I think we have like 15 minutes. Let's quickly mention the introduce. Binner. Before that, do you have any question? We almost finished the discussion for photon or quantization or gauge invariance, all these topics. Are there any questions about the quantization of photons? Of course, for those students who are interested in this different gauge, if they carry this gauge to do the quantization, you can also do that.
So for Feynman gauge, can we write down something similar constraint on A mu?
On A mu? For Feynman gauge, you can check. For Feynman gauge, this term disappeared, right?
Yes.
And you only have G mu nu over P squared. And for photon propagator, you will only have this, right?
Yeah.
Yeah, you can check yourself. For sure, contract with P mu is not enough to carry it. Yeah, it's just a different gauge choice. It's a different gauge choice.
我意思就是有没有像罗伦兹 gauge 一样，我能写一个关于 A mu 的这么一个
That's your question. I see. It's not for sure. It's not a precise Lorentz gauge. It's something else. Yeah, you can try. It's a good question. Yes.
Why is it inconvenient to compute the propagator if there is if there is就是后面那一项不存在的时候，为什么这个传播子就算和说就它 e 就不存在，就 a box a 为什么它 e 就不存在？
Because sometimes a matrix does not have inverse, right? You learn in linear algebra, right? Right?
Yeah.
Right? If it's with one, which condition does anybody remember? In which case the inverse does not exist.
What's the key point of this of its inexistence?
Mathematically it's very clear, right? It's just the inverse does not exist, or in other words, maybe if I remember correctly, the determinant is 0. Meaning there's some for that negative, there's some degeneracy.
Can we notice this? Can we notice this by imposing psi to infinity?
Can see it equals to infinity?
Yeah.
That's a very, very good question. You can see from here. But the point is, okay, let me try to clarify. If you look at this propagator, then if we take a c equals to infinity, again, this blows up, right? So it's not quite useful. Not quite useful. This essentially means this actually explains why it does not exist. If you insist it's not infinite. So you may want to ask physically why. If you let me make the logic even clearer. If you take this 2-point or photon propagator literally really physical object, then you maybe get confused, right? Because you may ask, well, you just tell me that all the physical quantities are not depend on the gauge choice. Now you're saying that sometimes when I take let's say c goes to infinity, this quantity is ill behaved, okay? So what's the point? What's the point? The point is as follows. The point is you shouldn't take this too much as a physical observable, okay? Right? Because A itself has ambiguity. Remember that, okay? A is not a physical variable. So you shouldn't take a 2-point function of A too seriously. Let's say this is almost the observable. That's not true. This 2-point function is only an intermediate result, not yet the final physical result. To really measure to get the final physical result, you have to let this photon participate in some amplitude process. Okay, let the photon scatter with electron, for example. Okay, eventually compute something like S matrix. Then you will see there's no confusion. Okay, that's the explanation. And maybe regarding to that question, what about c equal to 1? To see c equal to 1, well, the cheap way to say is just take c equal to 1 here. Okay? So for c equals to 1, you only deform this Maxwell Lagrangian by the half of this partial A squared, okay? By this term, a particular value for c. You can define that kind of gauge fixing by deform the Lagrangian, right? As I said, you can do different level of fix. You can fix in your equation motion level, or you can also fix in the Lagrangian level. In fact, you will see when you take a c equals to 1, you get a new equation motion here. Okay, right? You see, you get a new equation motion here. The new equation motion is nothing but this equals zero. You see, c equals to 1. This term is gone. Okay. This is the amount. This is the amount to you. You see, this is the amount to for the original Maxwell equation motion. You throw away this term, or you impose this is equal to 0. Right? See? If you only want to achieve the result, say, I want to take use of the gauge fixing condition like a Lorentz gauge at the equation of motion level. I want to simplify the equation of motion. Then cos A equals to 1 does the job. Okay? Okay? But only for this step. But this doesn't mean you need to check, prove or disprove. Doesn't mean this equals to 1 completely equivalent to this one. In order to check these two equivalents completely, you have to go through all the steps, even after quantization. Right? Yeah, it's a little confusing here, but I think we can take a priori. These are the different gauge choice. These are the different gauge choice. In order to try to build the relation, you can check it. You can check. So for Qc equals to 1, anyway, the short answer is for Qc equals to 1, take the deformation by this term to the original Lagrange. It's the definition of this new gauge. You can think in that way. But for the question whether this gauge is related to Lorentz gauge or in what step is related to Lorentz gauge, you can check through. At the equation of motion level, equivalent to you take original equation of motion plus this one, you get the new equation of motion. And new equation of motion is equivalent to you get from this new Lagrange one. So this is completely equivalent. For the short answer is at the equation of motion level, Qc equals to 1 is equivalent to Lorentz gauge. You can check it. Okay. For others, you have to go through in order to demonstrate whether it is completely equivalent. Okay. So any other question? Yeah, let's leave the spinner to the next. Yeah, we have 5 minutes. We were going to have the middle term examination 2 weeks after. November 4th, right? Everybody knows that? Everybody knows that? Good. We have 5 minutes question answer time. Q&A time.
问一下，就是那个往上车辆后面加那个我主要怎么干？拿那个拿一次
把那个可再生零入场，要求它那个运动方式就能得到那个。
That's right. We are waiting for that one. Then we can take it from. You are right. You take this one or two cassette. You will feel.
相当于是一个
那你是说我对于可赛做 EOM 对是可以得到的一个 gauge 的 constraint。
Yes.
这就是零入场。
This is the reason why we. In that sense, this is a good choice. 还有别的问题吗？
你这只能算那个就这坨的离离特性就是知道或者这坨的过程。
就是离的话，你可以是原是 A， 好了大。
哦，我不知道，所以说这个啊，那个本身懒人应该就是天上。
那如果你这样说的话，那说是不是那个小气？
我的，
飞曼是挺危险的。
飞曼对飞曼就是
好的，你刚才
我理解意外不知道它的话，它也便宜点。
对飞曼它也是个老人，
也就是说我
快
还是建立一个而且这个形式的话，然后
又开始微调，
这个变换绝对无对吧？
我对面被要求就全是。这个不是打呀，我稍微知道。
因为我觉得A 的
好的，他的
假如我们然后对吧，就会得到这个就是他现在普通话想变成3个句吧，咱们的意义，对，他想比较专业的，所以如果是吧，不让别人是。
很好，这是哪一个包？
头上面的零里切开，相当于你把零给它零回去，就是你先把这个取得可赛这个情况下，和零可赛为的取点，大概资源是说还是还是
那这样子的话，不管怎么样，不是都是要求他是
飞曼要也很不一样，也是这个人物非常这个的话，是不是也是这个不，他们一样的呀，也不是，只是他零可赛等于是简化计算了啊，
所以那个要
这个道理吗？是这个。
对，我一个可以，
那还说这个对着它压不住所有队，还能
压不住所有，一个压不住，一个人这个地方压不住，
哦，就是这个对着是压不住所有队，所以那个可赛是另外一个。
对，啊不，你在另外一个
不是可赛的本身，你定可赛是能够感觉可能不是本身，
本身加了一个新字，加了一个，
可赛原是不行，就是把那个
如果是什么质量，
但是现在
也就是先变量的做符就加一下这个，一般只需要那个符给的人。
那这样子的话，它不是一般的话取放在这里的。哦，我从右
可以，我知道可以，你可以取一标过去，但你只要是在认为是个场面上就不好了。
我从 UM 看的话，比较好，这个楼可以说，你看来取个关键是贝斯他们的任意的一个都行，刚上场都是可以的。
可以讲的第一个，
他就是那个，你要把它当成主力团就好。这个是他不管你，不要认为他是就是他也是一个拉伸，他也是一个材料。
那我引入这个
这个，对，他就是三个往上走吧，他就把约束变成额外的约束。
对呀，那这样你和 C 你取什么肯定都一样的。
哦，对，那就我就是把罗伦兹 gauge 直接给他喊到那个变峰里面去了。哦，哎，那我为什么不能加？为什么我不能？为什么我非要放分？你知道吗？直接2分就是你不是就会就是规范了，它是写啊，对不对？那我就给它放上面，不是就不会有
费曼当初是这么写的，费曼当初是这么写的。
他为什么要放分母上？
你们理解为什么是这个吗？
对，这个就是很 C，
这个很奇妙。
对，但是 当然是我们这种人可以指它这个是比下面是个次。
一的话是
你看，你这个格式一取零和一就是为了简化计算的嘛。但如果是你如果是看那个物理关系的量的话，是可 C
高的3个的话，
这它是不是也可以 depend on space time？
那这像在总的话，
这可以 depend on space time。从 UM 看好像是可以的。
但是这主要是这个数据是这一项第三个。现在我是第三个，因为只有这个东西知道。
我意思就是它不只是 arbitrary constant， 还可以是
现在
变量。
对，你可以是个 arbitrary field，depend on space time。
这个东西
把这个项加进来，
它不是它有一个里面有一个第三个它 x 第二个函数 t， 它是因为它第二个函数里面就是你那个洛登斯，
然后
AMU，
然后
第二个可 C
一样的地方。
对对吧 ？T N 成高是几个20几个，那它就相当于
它章面上的那个是
加个最像
算一下它哪里？为什么是？
算一下它普遍的微信。
对啊，因为它这个
有看在书里面，它有一个 E 是从哪来的？看你看那个书里面无穷那个
无穷未来
那个什么 P 什么东西，
我说它引它个 E 并不是要求它是一个是有一个电荷的，
它要这个变量。
全部加这个
这个一是电荷。
然后
那是 Q 我这个在想，要是会把一指数搞个指数出来，我是
不是我说拉个不了。
为什么可以加进来呢？因为 A 达个正无穷是在。
我知道它原来的形式，
它原来要把后面 A 达个。
我也在想这个一到底是啥。
原来的形式是一个电荷，
对吧？对。
那
为什么这边一软一修了变量？
对，因为它是不能这个之后，
自然单位自然单位
原来
如果是 arbitrary 的话，就要求后面
Q 的为什么 Q 可以标记一个人？
但是我们要当如果忽略它是这个是变的话，
就是一直上面 E 啊，
它是所以上面就不到位，
就从那个老师
规范这样
我当时理解这个
但是 P 要求 U 不管中间的 operator 一定要在最
现在就这个 P3里面的假定 U1 的表示嘛，很像，表示不是这个样，P3考虑这个，然后你 P1 考虑这一项，这是它的一个表示，你随便调嘛。
因为他们接的对我对一相对于零，因为它一个是这标记 P3，一个 P3，他们两个不一样，你只有在两个 P 一样的时候对应才会出问题。其他是随任意交换。当然，我是专门的里面，不同的 P，
P 与 P 接 P 与 Q 的原来方式。P 不等于 Q，
那就比如说，就 P 不等于 Q，
不是那种什么没有在讲过这件事。
就是它那个特莱因高能场，特莱因高能场，它这个里面的意思，只要是 P 不等于 Q， 意思就是这个。如果 delta 的 P 减去
啊，但是 P3跟 P 如果相等的话，
但这里是不谈，
这里是不谈，为什么要记一些？它这里是考虑是两个不同的入射或者。
你可以认为就是你可以认为
没有啊，应该是没有入射，我是经常是动量嘛 ，P
不会表示
跟这个出射，
这里面本来就不会。
然后说它不等它肯定是交换。
这么的能比？
如果没有一个这个考虑不等，
所以它基本上不会想。
入还是出？
这个
我也要再
相等于相当于没参与这个过程，你把它丢掉，是吗？真有可能。
它有单位区，单位区，有可能有这种情况。
是什么把丢掉就好了？你刚刚用字，然后在它卡分。
不等的那就没问题，但是有可能是相等的。
这都这方程与单位区认。
对，你比如说，我们就考虑一个一直进的，然后有比如说，
因为它
是等的嘛。 那而且
反正
中间
直接可以用 Q 来标记，是这个意思吗？就和来标记。
这个差别是没有的。
咱们啥学当时拉个老师？
S matrix you，
那我如果用标准拉个老师发我，
所以我们可以看过的都有。